Hello. In this lesson, we're going to take a look at percentage yield. The percent yield is a way of measuring how successful a reaction has been. Calculations are made to determine the success of the chemical reaction because most reactions do not succeed in producing the predicted or maximum amount of product that they had. And this is mainly because no matter how well you measure something or no matter how well a scientist is at creating the chemical compound, there will always be a little bit that's either left unreacted just due to the nature of the chemicals themselves. Either they can't get to it by space, there might be just some left on the side. The inherent way we measure always leads to some uncertainty with how much we can produce. The percent yield is therefore a good way for us to not only just judge how successful the reaction is, but also for us to be economical with how much we produce. To get the percent yield, we take the actual yield we got, so this right here, the amount we measured in grams or moles of how much we had, and we divide that by the theoretical yield. So using our stoichiometric quantities, we can figure out how much we should have got, and we times that by 100. So it gives us a nice round percentage. This doesn't always mean that 100% is good and like 20% is bad. Some reactions, they might only have a maximum yield of 30%, and that's actually considered very good. Others, if you get less than 85%, it's actually considered bad. So it depends on the nature of the chemical system itself. Also, if you have a multi-step synthesis and we have 90% yields for 5, 6, 7 steps, our overall yield will actually be rather low from steps 1 through 5. It might only be 30% because we're getting 9% of 9% of 9% and so on. So, a couple of things. Theoretical yield, maximum amount of product that I can get from a given amount of reactant. Actual yield is what I get from the experiment. And percentage yield is the ratio of the actual yield to theoretical yield as a percentage. So let's take a look at a calculation. So for my first example is if I burn 10 grams of methane in an excess of oxygen gas, and I only get 19.8 grams of water, I would know what my percentage yield is. So first of all, after I balance my chemical equation, which I've been nice enough to do for you, well, I have to figure out what's limiting and what's excess. Well, in the questions already told me excess is oxygen, so that takes care of that. So now I have to find out how many grams of water should I have gotten from 10 grams of methane. So I'm going to first calculate the number of moles of methane from 10 grams. So NCH4, 10 grams over 16 grams per mole for methane, and that gives us 0.63 moles of methane. I'm going to use my mole ratio, so my known one in this case is 2 moles of H2O for every 1 mole of methane, because I'm trying to figure out how much water I'm going to make, or could make. So X moles of H2O, and I have 0.63 moles of methane. Cross multiply, and I'm going to get 1.25 moles, and that's equal to X moles of water. So I know I'm going to get 1.25 moles of water, but in the question I'm given grams, so I'm going to have to convert from my number of moles of water to grams. So mass is equal to number of moles times molar mass, which is equal to 1.25 moles times the 18 grams per mole for water. Units moles can't cancel out, and I'm left with 22.5 grams And this is my theoretical yield. Theoretical. So that's my theoretical yield. So my actual yield up here, so I have to divide my actual by my theoretical and multiply it by 100. I'm just going to partition off some space. So percent yield is going to be my actual over theoretical times 100. So 19.8 grams over 22.5 grams times 100, and that gives me 88% for that particular reaction. So not a bad reaction, 88%, 19.8 out of a possible 22.5 grams, pretty good. So just like all these other questions, we're using the mole ratio as a way to convert from one quantity to another. So I wanted to find out how many moles of methane, or the number of moles of methane that I would need for this amount of water. And I use that then to get my theoretical yield. So all the time we're going to use these mole ratios. That's why they're so important. They allow us to convert from one side of the equation to the other. So let's take a look at this slightly more difficult question. I have 25 grams of phosphorus, P4, and 50 grams of oxygen, and I combine them to make 42.5 grams of tetraphosphorus decoxide, P4O10. And I just want to know the percent yield. So, first thing I have to do is I have to find which one is limiting. Which one is my limiting reagent? Because that's going to determine how many moles I could possibly make of my P4O10. Is it going to be phosphorus or is it going to be oxygen? So let's first figure out the number of moles. So N for P4 is going to be 25 grams, and the molar mass for P4 is 155 grams per mole. That gives us 0.16 moles for P4. All right. For oxygen, number of moles, O2, I have 50 grams divided by 32 grams per mole of O2. I get a grand total of 1.56 moles for this. So between them, I have to figure out what's limiting and what's in excess. So I'm going to take my known ratio in this case. I have 5 moles of O2 for every 1 mole of P4. So if I used up all of my P4, how many moles of O2 would I need? So I have 0.16 moles P4. So I'm going to cross multiply, so bring this up over here, so it's 5 times 1.6, and that gives me 0.8 moles equal to the moles of O2. So I need 0.8 moles of O2 if I use up all of my P4. Well, I have way more than that. I actually have 1.56. So this is less than what I have, therefore it is in excess. And P4 is my limiting reagent. So, because P4 is my limiting reagent, that is the mole quantity I'm going to use to try and figure out my theoretical yield. So I'm going to compare P4 to P4O10, and I have a balanced chemical equation, which I did right before, P4 plus 5O2, which is where I got that ratio, gives me P4O10. But I'm also going to notice that my ratio here is 1 P4 to 1 P4O10, So that means that if I have 0.16 moles of P4, I'm going to need 0.16 moles of P4O10, or I'm going to make 0.16 moles of P4O10. So now that I know the number of moles of P4O10, well, just got to convert it into a mass. N times molar mass. So that's going to give me 0.16 moles times the molar mass of P4O10, which is 315 grams per mole. And that gives me a theoretical yield of 50.4 grams. So my theoretical yield has been determined. And I determined it first by applying the limiting reagent, then using my mole ratio, which is just 1 to 1 in this case, makes it pretty easy. Then take the number of moles, multiply it by the molar mass, and I have my theoretical yield at 50.4 grams. For my percent yield, well, that's going to be actual over theoretical times 100, and I'm just going to continue on this line. So it's going to be 42.5 from my question, grams, 50.4 grams, which I just figured out as my theoretical yield, times 100, this up, and I get a grand total of 84.3%. These questions are going to be our longest type calculation questions because we have to first use a limiting reagent, then we have to convert back and use our percentage yield to figure out how much we got. So these will generally be the longest types of questions we will experience this year in chemistry.